All right, section 6.2, we're going to deal with quantum numbers, and this is going to be a review from everything that we talked about in chapter 4 last year. So this is taking chapter 4 and really putting it into a single nutshell. So we're going to talk about quantum numbers and finding the electron, because as we all know, it's all about the electron, baby. All right? That's the key. Electrons interact. That's how chemical reactions happen, so we want to find the electron. So let's review a couple individuals who had some very important additions to figuring out quantum numbers. First is Heisenberg, and he showed that we can know the momentum of a particle, all right, using Planck's energy equation and all the stuff that we talked about in section 6.1. All right. However, the uncertainty principle states pretty much the electron is so small and so fast of a speed that we really don't know where it is. So in many cases, we are entirely uncertain about where the electron is. So if we can't find the electron, how are we going to know it's reacting? Well, to solve the uncertainty principle, which is Heisenberg, Schrodinger comes along and mathematically applies both the wave and particle nature of light into his equations, and this is known as quantum mechanics. And what he does is that if you see on the right here, each blue dot represents the probability that the electron will be there. Well, if you start going through and figuring out different energy levels, you can see that there's a very, very high probability that that electron in this example is right here. All right, now that is called an orbital. And then that's what we're going to start talking about here. So he can use the wave equation, gives us a probability of where the electron is going to be. And in this example, it's circular. Now, remember, solving the wave equation gives us a set of wave functions or orbitals and their corresponding energies. Now, remember, orbitals is the most likely region where the electron is going to be. Orbitals last year also were S, P, D, and F. And remember that sheet from section 1 that I showed you, same thing applies here. Now the difference last year, all we went into last year was there were 4 sets of quantum numbers. And I may have given you something like this. 6px. Right? 6px. All right, let's go through. I'm going to clean this up a little bit, make it look a little nicer. 6px. This is what we did last year. All right. What does the 6 represent? Does anybody remember from last year? The 6 represents the energy level. All right. P represented the sublevel. The X represented the direction or the axis that it was pointed on, so you had an XYZ probability. And then there was a 4th quantum number from last year, which was spin. And does anyone remember how many different ways an electron can spin? 2, clockwise and counterclockwise. So that is the extent in which we went into quantum numbers last year, was like 6px. Now, when we use quantum numbers, and there are actual numbers that can represent every part of the quantum equation. So each orbital describes a spatial distribution. It really, right here, this dot is saying these orbitals show the probability of where the electron's most likely going to be. And we describe these orbitals using quantum numbers. So there are 4 quantum numbers. The first quantum number is the principal energy level. Keep that in mind. Or the principal quantum number or principal energy number. All right, we can do energy. All right. Principal quantum number or principal energy level. It's represented by N. That is when I gave the 6px, the 6 is that number. So N can represent any number 1 to infinity. So when we say N, we're replying to the principal quantum number. So N is that. That's pretty straightforward. That can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to infinity. Now last year we usually worked with just 1 through 7, but it can go 1 to infinity. So n is a principal quantum number. The second number is called the angular momentum number. The angular momentum number. And we're still using numbers here. We're still using numbers. However, these numbers really help describe the sublevel. So, L, here it is. L can range anywhere. L equals anywhere from 0 to n minus 1. Well, what does that represent? Well, let's say my energy level is 3. So n equals 3. That means that L, my angular quantum momentum number, could be 0, 1, or 2. Because it's going to be 0 to n minus 1. 3 minus 1 is 2. So it could be 0 to 2, which means that when I have an energy level 3, my L value could be 0, 1, or 2. Now to translate, we use these numbers, 0, 1, or 2, really represent the shapes of the orbitals. So what does 0, 1, or 2 mean? 0 represents that it's an s orbital. 1 represents it's a p orbital. 2 represents it's a d orbital, and 3 represents it's an f orbital. So if we go back to the last example that I just had, it stated that our energy level was 3. Well, L is equal to 0 to n minus 1, which is 2. Which means at the third energy level, we can have 3s, we can have 3p, and we can have 3d, which is true, right? Absolutely. If we change that and we say n is equal to 1, our first energy level, what's the only sublevel that we can have in our first energy level? S, right? Well, this goes and proves it. L is equal to 0 to n minus 1. Well, what's 1 minus 1? 0. What's the only angular momentum or sublevel that we can have at energy level 1? S. 1s. So, the second number is the angular momentum number. Angular momentum. So we have principal energy or principal number, which is represented by n. We have the angular momentum number, which is represented by L. And L corresponds to sublevel. So if I went out, if L equaled 4, that would represent G, because G is my next orbital after F. All right, third quantum number is the magnetic quantum number. And the magnetic quantum number describes the three-dimensional orientation. So this goes, remember when I gave 6px last year, we talked about they're pointed in the x, y, or z direction. That is this three-dimensional orientation. But we are going to use numbers again to use that and apply that. So M is the magnetic quantum number. That is equal to negative L to L. Since M is greater than negative L, but it's less than positive L. And we get L from the last slide. L is the sublevel. The 0 is S, 1 is P, 2 is D. We get that from the last slide. So we kind of have all right, something like this. So if we continue to use our example from the previous slide, n equals 3. That means L is equal to 0 to 2, which means the maximum value for L was 2, which means that in this case, M, our magnetic quantum number, can be greater than or equal to negative L. Well, the greatest value for L was negative 2. So M can be negative 2, negative 1, 0, 1, or 2. So, all right, it's greater than or equal to negative L. So negative 2, negative 1, 0, 1, and 2 are all greater than or equal to negative 2, and they're all less than 2. So I have a range from negative 2 to 2. Since 2 is my highest possible value for L, my range is from negative 2 to 2, and my whole numbers in that are negative 2, negative 1, 0, 1, and 2. Now, if I do another example, and if I do another example here real quick with this quantum number idea, all right, and I say n equals 1. N equals 1. Well, remember, L is equal to 0 to n minus 1, so L can only equal 0, which means M, in this case, can only equal 0. So they're going to kind of show you the magnetic quantum number. So if we get a chart here, this chart can kind of give you the idea of how each energy level works. So you have n equals 3. Possible values of L are all the way up to 2. Now I just kind of want to explain something here. Do you see how when we did configuration last year, 1s had 2 lines, 2s had 1 line, p had 3 lines, d had 5 lines to represent the orbitals? These numbers represent that. Look at s. Right? The value of L is 0, which means that the value of M is 0, which means that you have 1 orbital. Same thing for 2s. If you go down to 2p, however, 2p, possible values for L are 1, which means that we have 3 values for ML. Well, how many orbitals do we have for P? 3. Go down to 3D. How many orbitals do we have? All right, 5. How do we get that? Plus or minus the values of L. F. F has 7 orbitals. Well, how do we have 7 orbitals? Well, the value for L is 3. Plus or minus 3 gives us 7 different combinations. So that is kind of how the magnetic quantum number can work. So those are 3 of the 4 quantum numbers. So here's what an orbital looks like. Here's what an s orbital looks like. It's a circle, so it's not really arranged in one way or another. All right. I'm not going to worry about this slide. P orbitals. Now, P orbitals look like an hourglass. There's 3 possible arrangements for a P orbital, which makes sense, X, Y, and Z. We can go to D orbitals. Right? Then there are 5 arrangements for D orbitals. And we will talk about those. All right, last thing that I want to get is the magnetic quantum number. Or sorry, not the magnetic, the spin quantum number, which is the 4th quantum number. And remember that the spin of an electron can only go 2 ways. So when we talk about the spin of an electron, the value that we can give is plus 1/2 or minus 1/2. There are only 2 values for the spin quantum number. So that should kind of give you a general idea of how this works and how quantum numbers apply. So remember, if we go through the 4 quantum numbers, N is represented for the principal quantum number, the energy level. L represents the sublevel. And L is equal to 0 to n minus 1. M is the magnetic quantum number, and that represents negative L to positive L. And then there is spin, which simply is plus 1/2 or minus 1/2. Those are the 4 quantum numbers that we will continue to work with.